All right, let's get started. So assignment 2 is mostly graded. If you handed me a paper copy, I have them here. And I'm going to mail back the PDFs, annotated PDFs, like over the course of the afternoon. Assignment 3 is due. Assignment 4 will be out probably tomorrow. I'm behind on the lecture notes for these next two, for these last lecture and today's lecture. Okay, so what I want to do today is continue with the investigation of the functional programming part of in the linear logic. And so that was a message on the linear logic list, okay, which sort of spoke from my heart as well, okay. So if you just write down a proof system like we did, and then you write down some reduction rules, right, that's not a programming language. That's not really even what I would consider a Kurout isomorphism. It's just a language for writing down proofs and doing reductions on them, okay. So when I would apply the word Kurout isomorphism is if there are some independently interesting computational phenomenon that you capture and you realize you can capture by the structure of proofs in a particular logic, okay. So the original Kurout isomorphism was that people had been doing simply type lambda calculus since Church, like in the 40s, okay. So they knew what a simply type lambda calculus was, and people had been working on that. And then Providence wrote that book in 1965 about natural deduction, and he had been working on natural deduction for a while. And when he was talking about normalization, there were these complicated tree operations like grafting one tree on another and those kind of things. And that was what natural deduction was. And then Howard understood that, or observed that those two things are really the same thing. The structure of proofs for natural deduction is just the structure of simply type lambda terms. Okay. So he established that isomorphism between the simply type lambda terms and the natural deductions. Okay. So that's one example. Another example is a student of mine, Rowan Davies, who was here for a few months and just left. So people had been thinking a lot about this notion of partial evaluation. Partial evaluation is this idea that if you have a functional program and you know some of the inputs before others, you partially evaluate your program with respect to the inputs that you know, and you get a residual program that accepts now the remaining inputs. Okay, and people have been worried about how to do this right. Okay, and there is some technique called binding time analysis, where you look at your program and you see, well, if I know this and I also know this, I can do this reduction and so on. But it was still very much based on just the operational semantics. There was no logic behind it. Okay, and then Rowan observed that, well, if I do temporal logic and I look at the structure of proofs in temporal logic and the structure of evaluation, then it captures exactly what partial evaluation is trying to do. Okay, so there's partial evaluation, then you realize, oh, temporal logic would do the trick, because in a linear time temporal logic, you can kind of do all the computation at phase 1. That gives you a residual program. Now you can do all the computation at stage 2. It gives you a program at stage 3. So the staging in time as you go forward is the same as the staging of that happens in partial evaluation. Input at time 0, input at time 1, and so on. And you can therefore give now a nice logical explanation of what partial evaluation is. It's just proofs in temporal logic. Okay. But in both of these examples, we have pre-existing things or computational phenomenon, and then we find the logic that expresses it and explains it, clarifies, simplifies it. And similarly, before, what I talked about, the sequent calculus in linear logic, there people have been worried about these session-based pi calculus, where the way that the pi calculus communicates is with these channels, which have two endpoints, and there's a certain protocol that you have to obey on this kind of connection. And they've been trying to write systems, type systems, for describing how these should behave. And there are these type systems which actually have some aspects of linearity in it. But they weren't exactly in a Kurout correspondence. Then we observed that if you have a sequent calculus, you can actually put them into exact correspondence. And now you realize that linear logic, a sequent calculus for linear logic, gives you a correspondence with session-based concurrency. Okay. But what we've done with functional programming doesn't have that flavor at all. I wrote down the terms, and I told you when you reduce something, how you reduce things, but it's not a programming language. What's new here? We're just doing reductions. Okay, so there's different ways to approach that. So we'll see after the midterm in the second half of the course that there's some really interesting things you can do. For example, you can characterize through linearity the runtime complexity of your functions. So you can write down a type system and a logic so that the only functions you can write will be polynomial time computable. And conversely, every polytime computable function will be representable. Okay. So there's a lot of things to say, but it requires more machinery. Okay. So I'm going to pursue one particular way of trying to look at this problem. Okay. And this is simply connecting up the pieces that we already have in place. Okay. So what we already have in place is we have a sequent calculus, and we have a reading of the proof in the sequent calculus as session-based concurrent programs, okay, expressed in the pi calculus, but that's sort of one line. And we have a translation which shows you that you can take any natural deduction proof and translate it into the sequent calculus, right? So that was part of the proof. We were showing that if something can be proven, so we had a theorem that says that if gamma and delta in natural deduction we can prove A, then we can prove it in the sequent calculus. And the way we did that is we translated the natural deduction proofs here into proofs in the sequent calculus. Okay? So now I'm just trying to put these two things together. So, we put proof terms here. Okay? And then they translate into process terms, P over here. Okay? And we already know an operational semantics for the process terms. Okay? And so just by playing through the proof that we did, we should be able to translate terms in natural deductions, which are these functional terms, into process terms and see how they evaluate. And that induces an operational semantics on our original terms M. Okay. So this is, like I said at the very beginning, this is not the only way to go. But that's certainly one way to go if you're searching for an operational meaning for these terms. Okay. And we formed some kind of vague conjectures based on some intuition about what the operational semantics might be here for various things like lazy pairs and eager pairs and things like that. And we can just examine and see what happens when we do this translation to see if our intuition is validated or if it turns out the operational reading of these things is different. Okay. So if you step back a little bit, you can also think of this as giving a concurrent interpretation, okay, of a linearly typed lambda calculus. Okay, a concurrent semantics, because these are concurrent in a particular type of concurrency with the session-based concurrency. Okay, everybody clear what we're trying to do? Okay. Okay, so let's see if we can do that. Okay, so we should examine the various constructs on this side, and then see what they translate to. Okay. And then see what kind of semantics we get out. So let's do something very simple. Let's start with pairs. Okay. Okay. So I'm going to ignore the gamma for the moment. Okay, just so I don't have to write too much. Okay. So our rule here was something like this. We have delta, and we prove A with B. And remember that the introduction rule and natural deduction correspond exactly to the right rules in the sequent calculus. Okay. And that the elimination rules are turned upside down. So when we talk about the introduction rule, it looks like this. And so here we have a pair M, comma N. Okay. Okay, so now what happens when I translate to the sequent calculus? Okay. So if I translate this thing over here, I get delta, okay, and then I get some process P, and I have to decide on a name for the channel. Yeah, you have a question, Anton?
You meant the other terms now, right?
Oh yeah, sorry. This is going to happen multiple times today. Okay. Okay. Thanks. Okay. So remember that with the process terms, I have to kind of give a name to the channel along which P offers the service A. So I have to make up some name here. And that name doesn't occur already in delta. Okay. So what that means when we translate a term M, okay, we translate it with respect to a channel along which m is supposed to communicate its value. Okay, and so m, the translation of m is going to be p, and p is supposed to communicate its value or communicate with the outside world along the channel, which I call x here. Okay. Okay, so that's the translation of this part here. This part over here gives us q, okay, which also is along x. And then in the conclusion, I have delta, some expression which offers to the outside world along x a choice between a and b. And what is the process term? Yeah?
First, the type conclusion would be, right? And process term is a case.
Okay, so it's x dot case p q. Okay? Okay, so if I write this out somewhere, maybe I'll try to write it here. So the translation of m with respect to x is going to be some kind of p. Okay, and if m has type A, then x is going to be have type A. Okay, so that's what I'm going to try to define. So if I want to write this out here, how would I translate the pair m comma n with respect to x, according to what I have there? X dot case.
Translation of m with respect to x.
Mm-hmm.
And the translation of m with respect to
Okay, makes sense? Okay. All right, so this part's easy. Okay, so I'm going to give myself some room here. The interesting part is going to be the elimination rules, right? Because there the translation turns things upside down, so we have to think a little bit. So, okay. So, but over there, this is what you have to remember. Okay. Okay, so the elimination rule would say if we had delta, we have m, then we get in delta pi 1 of m of type A. All right. Okay, so now we have to think a little bit. And we want to translate into the sequent calculus. This is a theorem. For everything here, there should be something here. So this is the AND elimination 1 rule. So we get by induction hypothesis in delta turnstile, okay, some kind of a P. I'm going to call this, let's call it, actually let me call it x2. I don't think there's a problem with that. Okay, so I translate this m with respect to x will give me some kind of p. Okay, what do I need to get? I need to get some proof of A. How do I do this in the sequent calculus? Anybody remember how that proof goes? Yeah? Let's forget about the channels for the moment. Okay, just the proof that in the sequent calculus, if you have a proof of A with B, we can get a proof of A, which is this particular case of this theorem, right? So what we're trying to do is somehow get to a proof of A. Okay, how do we get to the proof of A? There's a certain...
Cut it again.
We cut it, right. Okay, so we apply a cut. Okay, a cut with a type A with B, or proposition A with B. So what we have here is A with B on the left-hand side, and we have A over here, right? Okay, so all the cases in the proof are very similar, right? So in order to model what the elimination rule does, what we do is we want to use the corresponding left rule. In order to give us a chance to do that, we cut with that formula, which makes it appear on the left. So we can now apply here the left rule. And the left rule is going to select A. And then we're going to conclude A. And then this follows by the identity at A. Okay, so this is the pattern of the proof. So now we'll have to just annotate it with proof terms to see what happens. Okay? Okay, so when we do the cut, this is going to be X. Okay, this is our convention that we rename these two the same thing. Okay, so what happens with the end left one rule? Anybody remember?
We have X colon A.
Yeah, so here we have X colon A. Okay, and so then the identity, okay, how does that work? Hopefully I haven't. We forward it to some other channel. Okay, so this is going to be X forward to W, W colon A. Okay, so here we want also W colon A. And what is the process term here? Right, we take X, do in left because we select the left component of that, and then follow it by X W. Okay. And then what is the proof term down here? So this is going to be on W.
Bind the X.
Hmm?
Bind the X and two processes.
Yeah, so it's a cut, so we bind the X and we put the two processes in parallel. So it's P, which depends on X. Let me make that explicit. In parallel with X dot in left, followed by X forwards to W. Okay? Are we okay on this? Okay, so the way we use this process, if you want to get the first component out, we send it in left. Okay, and then whatever we get out, we forward to W because we have to send out an A. Okay, and this P will offer us A with B. We give it the choice and forward the result. Okay, pretty straightforward. Okay, so that's nice. So now let's see what happens. Okay, so let's write down the translation here, just to be clear. So the translation of pi 1 of m with respect to a channel W. Okay, so what does it look like? Okay, new X. Translation of m on X, on that new variable that we introduced. X dot in left, followed by X forwards to W. Okay? So just writing out that proof. Okay, so if we had done the proof in all the detail last time, it wouldn't have required this much work, but this is just following through the proof. You have a question, Anton?
Ask the ability to do this kind of proof, it seems to be related to like invertibility, right? Is that related to which elimination forms you can have in natural reduction?
Well, we'll do tensor next. Maybe that'll answer your question because tensor is not invertible.
Right.
So we'll see what happens there. Yeah. Okay, so now we have the translation. Now the next thing we want to do is to get the rules of computation, we have to see in the natural deduction setting is how an introduction is followed by an elimination, right? So we introduce some kind of a pair, right? And then we take a projection of that. In the sequent calculus, it would be, a left and a right rule meeting. Okay. So let's see how we would translate if we have pi 1 applied to a pair. So pi 1 applied to the pair m, comma n. And let's translate this with respect to W. Okay, so we're just following our nose now, right? This should tell us everything that we need to know. Okay, so it's pi 1 of some term. So we get this part here. We get a new x. Then we get translation of the pair m comma n with respect to x. Okay, in parallel with x dot in left, followed by x w. Okay, so just by using this rule here. Now I know how to translate that, so that's the same as creating a new x. Then this pair gives us an x dot case. The first part is the translation of m with respect to x, and the second part is the translation of n with respect to x, and that's the end of the case. And then this is put in parallel with x dot in left, followed by x forwards to w. Okay? Okay, so now what happens here? Right, so we have an x dot in left over here, which selects a branch, and x dot k says here, choose a branch between these two. So the client chooses. And so this actually reduces to, okay, new x. Then we select the left part here, m x, and that's in parallel with x forwards w, right? Because we go underneath the in left. Anybody remember what this is, this particular pattern? Anybody has seen this before? What is this a proof term for? That's for the identity, right?
So it's a cut against identity.
Right, it's a cut against identity, right? Because this new x, two things in parallel like this, that's a cut, right? So it's a cut of this against the identity. And you can, of course, do this in the proof, but I'm not going to bother with that. I'll just know this is a cut with the identity. What happens when you have a cut with identity? Anybody remember that from the cut elimination proof? You can eliminate the cut and you just do substitution of names. So this reduces by one of these cut with identity reduction. And what does it do? Well, it substitutes w for x in this case. Okay. So what you end up getting is a translation of m with respect to w. Okay. Okay, so what does that mean? Well, the translation of pi 1 of the pair mn with respect to w is equal to, reduces to m, okay, on w. Is that surprising? Not particularly, right? But it's nice. Okay, because it says that the reduction rule we had before on the natural reduction side, that has pi 1 of the pair m comma n, reduces to m, okay? That actually turns out the computation that takes place if you translate this into the pi calculus, okay? And you let it go, okay? Because that's exactly what it does. So our suspicion that these kind of are maybe lazy pairs, okay? Let's see if that actually was true. So here the pair mn, to evaluate that, do we evaluate m and n? Well, not really, because it's underneath a selection on x. It's part of a case construct. And when you don't evaluate underneath some kind of selection, okay? So when you have a pair, indeed, it's lazy in the sense that we don't evaluate the components, okay? But when we select from it, okay, we get out the piece that we want, okay? And all of this, of course, is fully typed, linearly typed in the correct way, because it's all derived from the translation at the level of proofs. Okay. Okay, everybody on board here? Okay, so far we seem to have been betting correctly. Okay, and let's see how far we can get, what happens next. So let me do the other type of pair. Okay. Okay. So now things should become, they should be different in any case, okay, because it's a different kind of pair, so obviously. Okay, so let's try. So we have delta prime proves A, I should leave some room here, A tensor B, and that's the tensor introduction rule. We split it up, delta goes here, and gives us A, delta prime goes here and gives us B. And so this is an M of type A, this is an N of type B. Then the notation we used was M tensor N. Okay? Translate into the sequence calculus to see what happens. Okay. Okay, so first we do this on the proofs. Okay. And then, on the on the derivation, then we fill in the process terms, right? That's the way to do it. So by induction hypothesis, we get delta turnstile A, and we get delta prime turnstile B. And we know from our previous proof that we should just be using tensor R. And we get delta together with delta prime. And we should get A tensor B. Okay, so far makes sense, right? The introduction rule always gets modeled by the corresponding right rule over here in the translation. We have to label the output, so let's call it X. Okay, so now we have to think a little bit. How did we do this? Anybody remember process assignment? Yeah, Anton? Okay, we make a new channel, Y. And so that's the channel here. And that's going to be some process P. Okay? And then we send Y on X. And then we have P and Q in parallel. P in parallel with Q. Okay, so if I did this correctly, and you have to stop me if I didn't. Okay, so then this corresponds to some kind of a bound output, right? Okay, so that's good. So what would that mean? So let's write this down somewhere. Okay, let's do it over here. The translation of the pair M tensor N with respect to variable X equals okay, I think you can just read it off, right? So we create a new Y, and then send Y on X. And then we have in parallel, okay, translation of M with respect to Y, and N with respect to X. Okay? So that's what we get. Okay, so one thing we can observe is that how do we evaluate something which is an M tensor N? Well, let's look on the right-hand side. Well, we create a new name. Okay, that's fine. But then we do an output. Actually, nothing happens, right? Because you don't evaluate, you don't reduce under prefix for concurrent communication because it's a synchronous pi calculus. So you only start reducing these things. These start only communicating once you have found a matching partner for this output. Okay, so these pairs are also lazy. Nothing happens for a different reason, right? So already we were wrong, right? Tensor is not eager. Okay, it doesn't evaluate the pieces. Okay. So, all right, let me erase that. And let's see what happens with the tensor elimination rule. Okay, so this is what we have to remember from that part. Okay. All right, so anybody remember the tensor elimination rule? If you have a proof of A tensor B, how do we use that? So we have delta prime, and we have Y colon A, and Z colon B. We can get C. Then from delta together with delta prime, we can get C. Okay? And we had to do it this weird way because unlike with the pairs, we can't just take a projection, right? Because we must use both components of the pair. Okay. So let's remind ourselves of the proof term. If this is some M and this is some N, then what was the proof term for the elimination form? Yeah, so let Y tensor Z equals M in N was a proof of C. Okay. All right, so now we follow our program. we see how to translate this into the sequence calculus to see what the computation corresponds to. Okay, so induction hypothesis, delta gives us something of type A tensor B. Okay? What we're trying to get here eventually, down here will be delta together with delta prime, gives us C. Okay, induction hypothesis applied to the second premise. Okay, gives us delta prime, A, B, gives us C, right? So this is one induction hypothesis on the first premise there. This is the one induction hypothesis on the second. Now, how do I get the proof of C in the sequence calculus? Yeah, we use tensor left and cut. So the tensor left, you can see I've done this proof before, okay, because I left exactly the right amount of room, okay. And then we can do the cut and we get the conclusion here, okay. So now we just have to fill in proof terms for this, right? Okay. So let's say that we have a P X A tensor B. Okay, so then this would be called X. Yes? Okay. How do we name A and B in the premise?
A is Y.
A is some new Y and X is B. And this is going to be some Q. Okay. So what's our proof term here? I'll need room there. Okay, anybody remember for the tensor left rule? What does the tensor want to do? Right, so the tensor wants to output tensors in our environment, so we have to expect the corresponding input. So we input a y along x. Okay, and then the cut will just put a new x. Okay, put p, which depends on x, in parallel with x input y dot q. And this q depends on what? X, Y, and W. Okay, so let's think about that for a second. What does this actually mean? Can somebody give me a reading of it? Yeah? You send A out on X, on Y?
Yeah.
Okay. So it's a little weird, right?
It's a little weird, yeah.
Why is it weird? Because we think of pairs as being something very symmetric. But here the X plays kind of a special role. So we'll have to see if that disappears now when we look at the reduction. Right? Hopefully this weirdness will go away. Okay, so we're okay in this? So let's write down what the translation is. The translation of a let y tensor z equals, should I call it y tensor z? Let's see, what's the correspondence here? Y tensor x equals m in n with respect to w. Okay, so it should be create a new x. And then the first part should be the translation of m with respect to x in parallel with x input y dot q. What is q? It's a translation of n with respect to W and, okay, and they contain X, Y, and W, okay. Okay, did I do this right? Okay. All right, so we're just following our nose here. So now we want to see what the reduction works out to be, right? So let's get rid of this so I have some room here. Okay. Yeah? Well, the pair seems completely symmetric, but it looks like here that we're translating the pair with respect to x and then input one part of it, which is the first component. And what happened to the second component? Well, that's somehow tied to the name of x after it inputs the y. So there's some kind of asymmetry, right? A tensor B in the process calculus, right? If you, on the right-hand side, it sends a new channel y of type A and then behaves like B, right? It could equally well do the opposite, send some new channel of type B and then behave like A, but it doesn't. So there's an asymmetry. But in the natural reduction, we don't see any asymmetry. This seems like a completely symmetric thing. So we'll have to see now at the reduction what happens, okay? All right, so let's work out what the reduction is, right? So what we do is we say if we have let y tensor x equals m tensor n in, okay, some other r, something like that, okay, with respect to w. Okay, so what happens? So we have a new x. Then we have the translation of this m here, which is actually m tensor n. So it's m tensor n with respect to x. In parallel with x input y, followed by the translation of r with respect to w. Okay, stop me if I do something wrong, okay? Okay so far? Okay. So this is, of course, we're stuck here, so we'll have to do that. So what happens here is that we have new x. M tensor n should explode according to this. So we introduce a new y. We output y along x. And then we have in parallel the translation of m with respect to y and n with respect to x. And all of that is in parallel with x input y followed by r. Okay. Did I expand everything correctly? Okay. All right. So what happens now? Yeah, now we have a send and receive on channel X, right? Here's the receive, there's the send. We have to get the new y out to the front. So we get new x, new y. Okay, so I call both of these y. It was just a dirty trick, okay? But, okay, so what happens is that this y, which is quantified here, gets sent into here, okay? So really what I get here is just r, okay? What I get here is m, translated with respect to y, in parallel with n, x, in parallel with r, w. And if you had noted this before, r depends on x and y, in addition to w, so x, y. Okay, so what does this mean? Okay, so let's go and actually do the normal lambda calculus reduction. The lambda calculus reduction would say let y tensor x equals m tensor n in R reduces to, okay, m substituted for y, n substituted for x in R, right? That was our reduction there, okay, because that's the pattern. These are the terms, so we just plug in the terms for the pattern. So that's what we get by lambda calculus reduction, okay? This is what we get by pi calculus reduction. So what's going on here? Yeah?
We don't inline the true process and into R in pi calculus.
Right. So remember, the difference between natural reduction or lambda calculus and sequent calculus is that the computation engine, if you will, in lambda calculus is substitution, right? We don't have that available to us in the sequent calculus. We have to do things in small steps. So what do? Well, this m for y is just m sort of separately with a channel y that it communicates along. This n for x is just n separately with the channel x. Okay? So the variables, we don't substitute for them, but they will be expanded into channels. Okay? And tied to that channel will be n. So n will want to communicate along that channel x. And then the body of this is just r, which will communicate its value along w, but it also contains x and y, which are references to the variables originally, which will be references here to these channels x and y. Okay. So what happens is, of carrying out the substitution, we keep around the substitution in some sense, sort of separately. Okay. So what this means operationally is that when we have this kind of a let, and this thing has turned into a pair like this, okay, then from then on we can evaluate, we can step in parallel m, we can step in parallel n, and we can stop the body. Okay. They can all make step forward. And they will sort of synchronize, or can you come to variables? Okay. If the variable x here is needed somewhere, right, then we have to communicate with m, okay, or whatever m has reduced to, okay. And basically what will happen is that m is ready to communicate essentially if it's gotten down to a value. So if it's a lambda expression, then it will turn into an input, for example, and then r will want to send it an output, and the two can communicate, okay. So what's really going on here is that we don't do the substitution, but we just associate the term m with the channel y and the term n with the channel x. And now we can do things in parallel. Okay. So this kind of evaluation has a lot of special properties because of the linearity. Okay. So we know that x and y actually occur linearly in R. So there will be exactly one time that the evaluation of R will reference this n. And only exactly one time will reference the m. So we're not doing anything unnecessarily. We won't actually reduce something here that will never be used because it will be used. Okay. 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 So the surprise when you work these through, the price for me was that the pairs are not eager. Those pairs, the tensor pairs, right? So just like here, you don't really evaluate this because it turns into a case. M and n are in a case underneath. Okay, here, m and n are underneath an output. Okay. So unless we go to something like an asynchronous pi calculus where an output can happen asynchronously, okay, we can't really compute m and n until we have a case construct that takes it apart. Okay. But once it takes it apart, then the pair is a parallel construct because the two components will be reduced in parallel with the body of the let. All these things can happen simultaneously and independently. Well, not completely independently because x and y, the channels, serve as synchronization points. Okay. Okay. Does that make sense? Okay. So we should at least see what happens to variables because we didn't actually talk about that. So what happens in the translation of variables? So if we have a variable x translated with respect to w, okay. Okay, let's go through our proof, right? This is what we always do. So we don't have to guess, right? So over here we have A proves A, and this was the hypothesis rule. Okay, and over here we have to show that x colon A, okay, we have a proof of A in the sequent calculus. What rule do we use? Identity. We have to call, what did I call it there, W? And what is the proof term? X forwards W. And so this translation here of a variable x is just identifies x and w. Okay. So basically the way you think about this is that this is a term which is supposed to communicate its value along w. Okay. And how do we do that for a variable x? Well, we just tie x and w together. Okay. So that communicating along x, along w will actually communicate along x and the other way around. We tie those two things together. Okay. So we should do functions, right? Functions should always be interesting. Yeah, I think I have enough time to do functions and bang, okay, to see what happens. Okay, so for the right rule, for functions, for the introduction rule for functions, we have A, arrow B. So we introduce a new assumption, y colon A, and then we have m colon B, and here we have lambda y dot m colon A or B, right? So that is the introduction rule. Okay, so the schema is always the same. Introduction rules turn into right rules. Okay, so we just have to remember what the right rule is here. So in delta, blah, delta y colon A. And then here we have B, here we have A, arrow B, and let's do it with respect to x. Okay. So we have some process P here. And what's the process here? Yep. So we input a y along x and then behave like P. Okay. In some sense, this is almost the easiest case, right? A function that inputs an argument is the same as input an argument. The only difference here is that we name it x. So here we just give it to it just by the very fact where we have it. And here we have to name it and then send it. But it's really the same thing. Okay. Okay, so if we write that down somewhere. Okay, see if I have enough room here. The translation of lambda y dot m with respect to x is input y along x, and then we have the translation of m still with respect to x, right? Did I do this right? I think it's still, yeah. That should be the way it is, okay? All right, so now the interesting thing is going to come with the left rule. Okay. So, or the elimination rule, let's say, which has to somehow turn into the left rule. The elimination rule says if we have delta m of type A, arrow B, delta prime n of type A, then delta together with delta prime gives us m n of type B. Okay, so by induction hypothesis, we get delta A arrow B. What we want to get at the bottom here is delta together with delta prime gives us B. Okay, so now how does this work? Cut. Thank you. So we're going to have some kind of x colon A arrow B here. And we're still trying to derive B. Delta prime. If it's going to work out to be that, that's going to be there. Okay, now always the idea is to turn the elimination rule into the left rule. So now we have it on the left, so we can apply the left rule. What's the first premise? something proves A. What proves A? You could cut again, but you don't need to. Because delta prime proves A, which is what we have by induction hypothesis. And on the other side, we have to get from x colon b to b, right? Which is the identity. And this is the induction hypothesis. And this is the other induction hypothesis. Okay, so let's put process terms in there. So this is going to be some p x. This is going to be w, w, w. This is x forwards w. Okay. What is this thing here? Should be some new y, right? Yep. So y colon a. So we have a q, which we get by induction hypothesis. And then what's the term here? So this waits for an input. To communicate it, we have to send an output. What we send it is a new y, which has type A. So we have new y. We send x that y. And then we have in parallel q and x forwards w. These two are in parallel. So maybe we can read it or write it here. We have a new x. We have p x in parallel with new y, output y along x, and then q, which is y in parallel with x forwards w. Okay? All right. So, what does it mean for the translation here? So the translation of m applied to n with respect to w is new x. What's the first thing? Is it m with respect to x? Yeah. Okay. M translated with in parallel with new y, output y to x, and then we have in parallel. What is q? Translation of n with respect to y in parallel with x forwards to w. Okay? Did I get that right? Okay, good. So now we just have to see what happens when you have a reduction, so we can get an intuition for what the operational semantics means. Okay. First, the good news is when we have a lambda, right, we don't reduce underneath, so that's kind of a value. When we have an application, okay, we have the function part, and it waits for the arguments on x, and the argument actually will send something on x, so that's good news. Okay. So we'll have to see what happens when we have a read x. So let's write it down. So if we have the translation of lambda y dot m applied to n with respect to w, okay. All right, so that's the bottom case, so that we introduce a new x, and then we have the translation of lambda y dot m on x in parallel with introducing a new y, outputting that along x, and then we have the translation of n with respect to the y in parallel with x forwards to w. Okay, so now we have to expand that part. So we still get new x. What is this thing? It's we input y along x, and then we have the translation of m with respect to x. If I did that right. And we put that in parallel with new y, x bar y, n, y in parallel with x forwards w. Okay, that looks promising, right? Because it should be a read x if I have a lambda applied to an argument. Let's remind ourselves of the beta reduction rule. Lambda y dot m n reduces to n for y in m, right? Something like this. Okay. Okay, well, let's continue here. The y floats to the outside. So we have a new x and a new y. And now we have this can output y along this channel. The names match up again. This is miraculous. Okay. So this becomes just a translation of m with respect to x in parallel with the body of this, which is n y in parallel with x w. Okay, can we simplify this? So what does this signify here? We're cutting against, there are two cuts, and one of the cuts is against the identity, right? So I can eliminate that. So that eliminates x, so I get new y, the translation of m with respect to w, in parallel with the translation of n with respect to y. Okay. Right, let's look at the thing up there. Does it match up? Okay, so the m here depends on y, hopefully. Yeah, because it occurs here in the body of that input, so this depends on y. Okay, so what we're doing is we're evaluating the body of the function, right, which is m. And in parallel, we evaluate the argument. And we synchronize along the variable y, because whenever the body refers to y, it's going to be tied to the value of n. Okay. So what functions correspond to, these kind of linear functions correspond to, is what is called futures, okay, in functional programming. So you first evaluate the function part down to a function in an application. Once you have that function, you evaluate the argument and the body of the function simultaneously, independently, synchronizing on the variable y. So that's exactly what we're doing here. We're evaluating the body of the function and the argument at the same time. And if the value of y is needed, then we have to wait until the argument computes all the way down to a value. Okay. Okay, so now there are some interesting things to say about this. Okay, so one interesting thing is that by particular scheduling strategy on this kind of parallel evaluation, you can get call by value. Okay, and that is if you just schedule these processes so that this will always get down to a value first, and then you go here. Okay, then you get call by value because you don't go into the body until the argument has evaluated to a value. Okay. If you schedule the body first, what would you get? You would get call by need because you evaluate the body all the way, and you wouldn't touch this until it's needed, and it would only be needed if you get to y in the body of the function. Okay, and then you need to make some progress here. Now it's a very strange call by need because there's exactly one occurrence of this argument. Okay, so we don't have to worry particularly about sharing here because there's only one copy of n lying around. Okay, but it is still this kind of linear call by need. Okay, and if you don't worry, the schedule is completely arbitrary, what we have assumed so far, you just evaluate m and n in parallel. Body of the function, the argument get evaluated in parallel, and synchronize only on references to the variable that ties them together. Okay, so now we see how substitutions are implemented in the sequent calculus, right? So the substitutions that happen here in the semantics are simply implemented by evaluating n and m in parallel. And the value of m is going to be tied to the channel y. So variables are translated to channels. Okay, so that's how it works. Okay, are you okay on this? Okay, so it's so functions and those pairs are kind of very similar, right? They exhibit the same phenomenon. Okay, which is that you don't carry out the substitution, and you evaluate the body of the let together with m and n at the same time in parallel, and you synchronize on the variables. And here you just do it on a single variable. Okay. Okay, so I think we should look at bang, and I think that'll be enough for the lecture today. Okay. Of course, we can write down this whole semantics without reference to the pi calculus, and that's something I will try to do next time. Okay. But now we know what the semantics should be if we think about the semantics as given by the sequence calculus for linear logic. Okay. Okay, so gotta make some room here. Okay, so the bang right rule, or the bang introduction rule, looks like this: gamma and the way we write this is that we reuse the type constructor, okay, as a term constructor. And so the bang m tells us that that term doesn't contain any linear variables. Okay. All right. So that should correspond to the right rule for bang, and part of that is pretty easy. Okay. So here we have x colon bang a. Okay, and here we have A. And now the question is, do you guys remember, okay, what kind of proof term assignment we made to the bang right rule? Which kind of process assignment? Okay. What does a process that offers bang A have to do? Yeah? Hmm? No, it's actually not a send. It waits for a new channel on which to communicate with a copy. Remember? You did it in the homework. Almost all of you got this right, so I know you knew it a week and a half ago. Okay. So we wait for a new channel, and we can communicate along that channel, okay, in P. Okay, so that's what the right rule is.
The whole thing's like got a bang in front of it or something.
Yeah. Okay. Okay. So what that means is that I guess I can get rid of the pairs now. That the translation of bang m with respect to x is bang x y translation of m with respect to y. Okay? All right. Okay, good. Next rule over here is the elimination rule for bang. Okay, so this is a little tricky. So gamma delta proves m bang A. Okay, remember how we eliminate that? How we take advantage of this knowledge that bang A? Yeah? Right, if you can prove something with A in the persistent context, like something C, let's call this N, okay? And let's label this assumption U, okay? And then, we also have a delta prime here. And then what do we get in the conclusion? Gamma delta prime. Okay, so we have to have some kind of decomposition, which is like a let bang U equals M in N colon C. Okay. All right, so now we need to translate this to the sequent calculus to see what that means operationally. Okay. By induction hypothesis, on the first one, we get gamma delta turnstile bang A. Okay, and this is going to be some P communicating along some X. Okay. Okay, how do we proceed now? Thank you. I've planted Rob so he can say cut 5 times in this lecture, and that's his whole job. Okay. Cut. Okay. So what does that mean? Well, we have gamma, we have delta prime x colon bang A, and we try to prove C. And then the conclusion will be just the right one, hopefully, gamma delta, delta prime, and here we have C. Okay. Now the problem is, how do you get this proof that we want to cut with? Well, remember, this is the bang elimination rule, so what do we expect to apply over here? The bang left. Well, it's on the left because we use cut, okay, thanks to Rob. Otherwise, we would have been stuck forever here. Now we have gamma u colon A, delta prime, C. Now, where did we get that? By induction hypothesis, okay, from that. Okay, so here we get some Q W colon C. What is the proof term for this? X for U in Q. And then down here, we should have nu X. And then P, which mentions X, in parallel with X for U in Q. Okay, we must be almost out of time. Yeah. Okay. Makes sense? Okay. So that means the translation of let bang U equals M in N with respect to W is nu X, translation of M with respect to X in parallel with X for U in the translation of, is it Q with respect to W? No, not Q. N with respect to W, right? Okay. Are you okay? So let's try to see what happens when we reduce. Right, so the normal reduction would just say if this is a bang M, so let's try what happens when we do that. So we have let bang U equals bang M in N. Okay. Okay. So first we apply this rule. So we get nu X, translation of bang M with respect to X, and parallel with X for U in N with respect to W. And then we get nu X. What's the translation of bang M? It's a replicating input, hopefully. So that's bang X Y dot translation of M with respect to Y in parallel with X slash U, and then N, oops. And then N translated with respect to W. Okay, does this reduce? Okay, it's a cut of a bang, right, with a bang left, and that turns into a cut bang, okay, by renaming. So that's the same as nu U bang u input y, translation of m with respect to y in parallel with n on w. Okay. So this is the step from a cut on a bang formula to a cut bang. Okay. Yeah?
I think you also still need another copy of the persistent surface.
No, because we haven't communicated yet. Right? Should there be some communication going on here? Yeah. Right. So, okay, so here we are. Okay. So what actually happens, okay, instead of doing the substitution, which we thought we might do, m for u and n, what do we actually do? Okay. So what we do is we evaluate the body, which is n. Okay. Right, so that's the body. And while we evaluate that, right, this mentions u. Okay. We may need to refer to the variable u, but we have something that has a rating for replicating input on u. Okay. So that we could get the value of m where we need it. So we need to see what happens with the translation of the variable u, which is the last thing I'll do in lecture today, in order to really understand what's going on here. But what happens is that basically the m does not get evaluated, right? So this is like sort of a border to evaluation, but we associate it with u, okay, which is the shared or persistent variable, and we go ahead and evaluate the body. Does it remind you of anything? Yeah?
Tensor?
It's sort of like the tensor, except on the tensor we didn't have this replicating stuff here, we just had this. So the difference is that in the tensor, because we didn't have this thing could evaluate, could reduce. Here it's blocked because it's underneath this replicating input. So that means that this n will actually not be evaluated until u is referenced in n. Okay? So what this corresponds to is the fact that this is like a copying interpretation, a call by name interpretation of a let. Okay. So every time we reference u, it turns out, we'll get a new copy of m. Okay. So we'll have to see how that works out. So that's the last thing we have to do. So that's taken care of. So m gets reevaluated for every time u is used. And u is an unrestricted variable, so it might be used multiple times. So m gets reevaluated multiple times. So in particular, if you want to do call by name evaluation, well, this pattern will appear. Okay. Okay, so let's look at the last case. So here we have a rule that says this. If you have no assumptions and we're trying to prove A, then if u colon A is in gamma, we can use that. Okay, u colon A. So now we have to translate that over here into the sequence calculus. So gamma nothing proves. Okay, so how do we do that? How do we translate the use of a shared or persistent variable in the sequence calculus? Copy, okay. So we apply the copy rule, we get a copy here of A. And what we're trying to prove here, of course, is A. And that's the copy rule. And once we have copied it, how do we proceed? Now we have identity. Okay, so if you call the copy, I don't know what should we call it? Should we call it Y? So then this would be Y corresponds to W. Okay, and here we would have, so what does the proof term here look like? Does anybody remember what that is? The proof term, the process term for a copy? We send a new Y, right? So we create a new Y, and we send it on W. And then in this case, W is just tied to Y. Okay. And that's going to be send it on U, sorry. U was hidden here because it's that hidden assumption. Yeah. Right. So we have here that U colon A is in gamma. So we send a new name to U, and that gives us a copy which has type A, which we can tie to W. Okay, so what that means is that the translation of a unrestricted or persistent variable U with respect to W is create a new Y, send that Y to U, and then, oops, that shouldn't be a bar, right? Should be a prefix. And then we have Y is tied to W. Okay? Okay. So now let's look at this again. In the body of N here, there's going to be an occurrence of U. Well, could be. Okay, or multiple occurrences of U. Wherever there's occurrence of U here, what do? We send a new name Y along U, okay, and tie that to the place where U is actually where we want the result of U to be. Okay. And so then when we send the new channel here, we get a new copy of this, and the new copy will communicate with the place where U was along the channel that we gave it. Okay. So every time we see a variable, we create a new channel, send it to this thing, and we'll spawn a new evaluation of M. Okay. So this is a copying or by name interpretation, because every occurrence of the variable U will spawn a new evaluation of M. Okay. So what we have found is that evaluation actually, there's a lot of parallelism in the evaluation. And so if ordinary linear function and a linear argument, once you have the function part, the body of the function and the argument will evaluate in parallel, communicating on that linear variable, synchronizing on that linear variable. Okay? And that is, because it's in parallel, it's something like futures. So it's not by name or by need, but it's by name or by need you can get by a particular scheduling strategy, right? So if you force the argument to be first, then it's by value. If you force the body to go first, it's by need, okay? And if you want to have, so that's shared, but all the evaluation steps in the argument is shared because you just do it once. And if you want a copying semantics, which is like a call by name semantics, then you have to exploit the bang because the let bang is the thing that will actually implement sharing, copying, right? Every time that nonlinear variable is used, you get another copy. Okay. And so what happens is if you have a function that's by name, the way you translate that is that, okay, actually, let me try to do that next time. So I'm not going to try to, but I think you get the intuition. And there were some surprising things about this. So one thing I found surprising is that the tensor is not really eager, okay? But once you have it down to a tensor and you have the body, then the two parts are completely on the same level and they evaluate in parallel, okay? And also functions aren't really eager. Function application isn't really eager because you do the argument and the body in parallel. Okay, you don't have to force any particular order in which they're being done. They can be interleaved arbitrarily. So perhaps it was naive to expect that this would be eager. Okay, it would have been more insightful if we had conjectured right away that this kind of thing should evaluate M and N in parallel. Okay, and that's the way it turns out to be. Except they don't get evaluated because we have the synchronous pi calculus until we need the values, until we have the channels along which the values will be needed. Okay, which comes from the let. Okay. So, okay, so this has at least a little bit more meaning than what we just talked about last time. These kind of substitution semantics is just a way of talking about how proofs reduce. But here now we have a real operational semantics, and it has a significant amount of parallelism, and that kind of parallelism was known before. So this is the kind of futures parallelism, except that it's disciplined by the use of the types and by the use of linearity. So I will spend a little bit of time next time talking about if you have just a functional language and you don't have linearity in it, how you then exploit this picture in order to implement different evaluation strategies for that. I'll also talk about how you can take this evaluation strategy, which we derived from purely logical principles, and how you can write it down now that you know what it is, write it down in a different way. And so we'll see what happens there. Okay, so again, the big picture here is the following. So we wanted to see what the natural reduction proof terms actually corresponded to in terms of an operational semantics. We already know how to give an operation semantics to the sequence calculus. So if you use our proof that you can translate from natural reduction to sequence calculus, that induces an operational semantics on our functional terms. And the interesting thing is that because our sequence calculus takes very small steps, there's no substitution remaining. But instead of substitution, what we do is we evaluate the thing that we want to substitute along a channel, which is the name of the variable that we'd normally substitute for. So it's a particular form of what's called explicit substitutions, which is kind of hidden in the structure of the communicating processes. Okay? Questions? All right, so so if you gave me a homework, I have it here. If you mailed me a homework, I'm going to start mailing them back this afternoon. I'll try to get out the next homework tomorrow.